This video will be on calculating wavelengths and frequencies of light. There is going to be one assumption, and that is that you know how to use scientific notation on your calculator. If you don't know how to use that, you probably won't be able to get the answers correct on this when you try them out for yourself. If you just search YouTube, go to YouTube and search for using scientific notation on calculator, you'll find all sorts of demonstrations of how to do that on your calculator. There's a mode on your calculator, if you have a scientific calculator, for scientific notation, and using that mode you do not have to type times 10 to the whatever it is. It's a better way of doing it. It stores the numbers as a single memory entry. This is the equation we're going to be using, and in this equation c happens to be the speed of light in vacuum, and it's a constant. And the f and that weird symbol there, which is the Greek letter lambda, are the frequency and wavelength of the light, and the frequency times the wavelength will always equal that constant. The constant happens to be, in scientific notation here, 3.00 times 10 to the 8th meters per second. Now that's an approximation, good to 3 significant figures is the way we would say it. The speed of light is actually an exact number, and there it is. So you can see how precisely that is determined. It's exactly that many meters per second. It's defined to be that, in fact. Now, we're going to need a little bit of help using metric prefixes, which is going to show up in a lot of these things. The way metric prefixes work is there will be a letter in front of whatever the units happen to be, and cm stands for centimeters. The units would be meters, but the c is a metric prefix that happens to mean 10 to the minus 2. So if you've got a number written down in centimeters, you can replace that c with times 10 to the minus 2. It's a multiplier, so 50.2 centimeters would become 50.2 times 10 to the minus 2 meters. Now, technically, leaving that written as 50.2 times 10 to the minus 2 is not scientific notation, but it will work just fine. It's equivalent to the scientific notation, and it'll work fine for punching it into your calculator. And that's what we care about here. Millimeters, that's a prefix. That's the first m is a prefix, the second m is a meter, and you replace that first m with times 10 to the minus 3rd, so 8.62 millimeters becomes 8.62 times 10 to the minus 3rd meters. You can also go the other direction. If you've got a number written as something times 10 to the minus 3rd, you can replace the 10 to the minus 3rd with a lowercase m for millimeter. Another one that may show up from time to time is nano. That's the lowercase n. Now, and it's in front of an s here, which would stand for seconds. So nanoseconds, you replace the lowercase n with times 10 to the minus 9th. Some number in nanoseconds, 35.6 nanoseconds, becomes 35.6 times 10 to the minus 9th. And so that's how those things work. Here's a table that shows the metric prefixes we'll probably be using today, and probably some other ones as well. The top row up there has how nano is defined, times 10 to the minus 9th. And there's an example of using it with a calculator, or writing it so you could use that in a calculator. The next one here, this prefix is a Greek letter. It's the Greek letter mu, and it's used to stand for micro. When you see that, you'd say micro, which means times 10 to the minus 6th. That means it's actually a millionth of something. And so 25.6 microseconds would be 25.6 times 10 to the minus 6th seconds. And again, technically that is not good scientific notation, but it works just fine for plugging it into your calculator, and that's what we'll be concerned with. Okay, and then we've already dealt with milli, the metric prefixes of M. Here I use it as a milli MK. K is the metric system abbreviation for Kelvin, so this would be 15.3 millikelvin. That would be a very cold temperature, and so you replace the lowercase m with times 10 to the minus third, and 15.3 times 10 to the minus third Kelvin is what that would be. Now a lowercase k is a metric abbreviation for times 10 to the plus third. And you might have run a 10K before or walked a 10K. That's shorthand notation for 10 kilometers. And replace that K with times 10 to the third and 10 times 10 to the third meters, which would be 10 to the fourth meters, which is 10,000 meters. That's an Olympic event, but it's also a popular road race distance as well. All right, a capital M is a million. It's pronounced mega, and so if you see mega on something or a capital M, you can replace it with times 10 to the sixth. So 47.3 capital MHZ, you would read that as megahertz. That's our unit of frequency we haven't dealt with yet, but that would be 47.3 times 10 to the sixth hertz. And then the capital G, pronounced giga or giga. Either pronunciation is okay depending on where you are in the world, but that means times 10 to the ninth, or billion. So if you see something like 2.4 gigahertz, replace the capital G with times 10 to the sixth, and you can put it into your calculator that way. 2.4 times 10 to the sixth hertz. Okay, here's our equation for the speed of light. F is the frequency, and we measure frequency in units called hertz. The frequency is the number of vibrations of the wave that happen every second, or the number of repetitions of the wave that happen every second. And it's sometimes a cycle per second is stated instead of a hertz. Now cycle is just a placeholder word. The hertz is actually just 1 over a second as far as actual dimensions are concerned, or sometimes you can think of it as just a per second, although we don't like fractions with nothing on top, so 1 over a second might be better. Or if you're comfortable with negative exponents, you can write that as a second to the minus 1, and either of those things will work. Sometimes the Greek letter nu is used instead of an F, and the Greek letter nu looks kind of like a V, looks more like a V than anything else. You'll sometimes see that. So back to the C equals F lambda. Lambda is the wavelength of the light, and that's the distance from one peak of the wave to the next peak of the wave. In the case of electromagnetic radiation, it would be one place where the electric or the magnetic field is at a maximum to the next place that the electric or magnetic field is at a maximum. And we'll measure that in meters or some multiple of meters with a metric prefix. Now with that equation C equals F lambda, because the C is a constant, it means that if we know the wavelength, we can find the frequency, and if we know the frequency, we can find the wavelength. And sometimes, if we happen to know the wavelength, we could figure out the frequency. It will equal C divided by lambda. If you just look at the top equation up there and divide both sides by lambda, that's what you would get. Or if you look at the top equation and divide both sides by the F, then you would get this equation, lambda equals C over F. And so we'll be using those equations here. Suppose you're told that an FM radio station's frequency is 99.3, and on that radio station they might repeat that number several times per hour, but they don't usually mention what the units of it happen to be. Now, if it's an FM radio station, FM radio stations have to broadcast in a particular narrow part of the electromagnetic spectrum, and the numbers that they state for that are always going to be megahertz, so millions of hertz. 10 to the 6th hertz you can replace the mega with. So this particular radio station has a frequency of 99.3 times 10 to the 6th hertz. What is the wavelength going to be? Well, that'll be lambda equals C over F equals 3.00 times 10 to the 8th meters per second divided by 99.3 times 10 to the 6th hertz. When I have a problem that involves units, I will usually try to evaluate the units first and make sure that I end up with something sensible for the units. And the units are the things like the meters per second and the hertz and stuff like that. And I deal with them algebraically as they must be dealt with. And so a meter per second over a hertz, I can replace that with a meter per second divided by a 1 over a second. And anytime you divide by a fraction, you take that bottom fraction, flip it upside down, and multiply. And so that becomes a meter over a second times a second over 1. And that will become a meter over 1, which is just a meter. And those are the units I would expect for a wavelength. Now, in this problem, the wavelength that we happen to get turns out to be 3.02 meters. That's only about 3 giant steps. So if you take 3 large steps, you'll have walked the distance of the wavelength of that particular radio station's frequency. Now, it's traveling along at a really high speed, 3 times 10 to the 8th meters per second, which, by the way, happens to be 186,000 miles per second. So it's not just standing still, but you can still get a feel for how long that wavelength happens. Here are some problems to try on your own. The answers will be at the end of this. What you should do now is pause your playback and try each one of these problems out, and then at the end you can check your answers. All right, I'm going to continue on. If you still want to work on those things, pause the playback. Going the other direction, calculating the frequency when you happen to know the wavelength. Well, in that case, here's an example problem of that. I have a green laser that emits light with a wavelength of 532 nanometers. What is its frequency? Here's how I would do it. When you know the wavelength, you divide C by the wavelength, and that will equal the frequency. And so on top, I'll have 3.00 times 10 to the 8th meters per second over 532 nanometers. Now, in those nanometers, I'm going to replace N with times 10 to the minus 9th, and that's something I can plug into my calculator. Now, what about the units on this thing? A meter per second over a meter. I'm going to take that meter on the bottom and divide it by 1. That will not change it. So I'm just writing it as meters over a second divided by meters over 1. Then I've got a fraction on the bottom. I can flip that and multiply. And when I do that, I'll have meters over a second times 1 over meters. The meters will divide out, and I'll have 1 over seconds. And 1 over seconds is hertz. So my answer is going to have units of hertz. And now you can plug in those numbers into your calculator. 3.00 times 10 to the 8th divided by 532 times 10 to the minus 9th. And you'll get 5.64 times 10 to the 14th hertz. So there's one calculating the frequency when you know the wavelength. And to repeat that process and give you some practice, here are 3 problems where you can ask or work on that. Pause the playback. I'm going to go on to the next slide in 5 seconds, but pause the playback, try each of these out, and see if you can get the same answers that I do. On to the next slide. Here are the answers. You can pause here and compare the answers here with what you happen to get. If you don't have the same answers that I do, it may be that you're not using scientific notation correctly, and so that's something that you might want to learn how to do on your calculator.